floor is yours.
In the title of this talk, let me first explain a bit of the context around it. So the context is automated software restructurings or refactorings. So we need to apply restructurings or refactorings to keep large-scale software maintainable. And you can think of examples like API migrations, like I'm switching a logging framework. That means I now need to rummage through millions of lines of code to find all the places where I call my old logger and then switch to that new logger. It's not feasible to do that by hand, so we want to do automated refactorings to accomplish that. But industry is still sometimes reluctant to apply automated restructurings. The obvious reason is, well, safety concerns. How do you know that after you've applied such an intrusive restructuring that it still has the correct behavior? But other reasons are, well, it's a big time investment. You need to hire or find a developer that is willing to implement this restructuring and then hope that they have even the knowledge to do so, because, well, the field of metaprogramming is not always that accessible to everyone. So in this talk, I will introduce a new technique that hopefully makes restructurings, writing your own restructurings, a little bit more usable than it's currently. So before that, let's introduce some background on solutions that already exist to make writing restructurings easier. And one of those solutions are concrete syntax patterns. Now, on the top lines, you'll find some rewrite rules that, well, apply some very simple restructuring. You have an assert true statement that checks whether two expressions are equal, and we rewrite that to an assert equals method. Now, the E1 and the E2 in there represent meta variables that can represent any expression on which you match. And the example below that with an if statement, well, that matches on superfluous equals true statements you may have found in practice already. So we can also restructure that to remove the unnecessary equals true from it. Now, this is concrete syntax because we reuse the syntax of the object language. And the object language in this case can be something like Java, or, well, any language that supports this kind of syntax. Internally, concrete syntax gets compiled to abstract syntax. So at the bottom of the slide, you'll see the equivalent restructuring, but using the abstract syntax of the language rather than the concrete syntax. And I don't think I need to convince you that the concrete syntax is a lot more readable than the abstract variant. Furthermore, if you want to write the abstract syntax variant, you need to know the exact abstract syntax structure of the language that you're using, which, well, requires time, learning, and, well, we'd rather use the concrete syntax. So concrete syntax is one way which we improve the usability of writing restructurings. Another another technique are called metapatterns. And metapatterns we just informally define as patterns that contain more than just terms with holes. So that's quite broad. There are some examples on the slide. So we have a disjunctive pattern where we can, well, say we can match on function calls that either match a functions named foo or bar. A descendant pattern below that. In that example, we match on function definitions of foo that anywhere in the body have a return statement that returns 0. So the / there indicates a descendant pattern. That means we are matching on that AST node or any of its descendants. Similarly, we can have sequence patterns to more fancily match on lists. But also, it can be more than just pattern matching. The pattern can also have some behavior to it, and that's what we can do with patches. So we can actually have some rewrite rule inside the pattern itself. And in the example there at the bottom, we match on function calls to foo, and we rename that to bar. And the nice thing about meta patterns is that we now inline a lot of logic that normally would be outside of the patterns into the pattern itself, making the code a little bit more concise. So now I've introduced two ways to make restructurings more usable. One is with concrete syntax, and this with metapatterns. Now, the contribution of this work is, well, can we embed the metapatterns in the concrete syntax, which we aptly call concrete syntax metapatterns. We're going to try to compile these concrete syntax metapatterns to abstract syntax metapatterns. Those are the examples that I've shown on the previous slide. I'm going to do that using black box parsers. That means that all I need is some parser of the language that you want to use, Java, C++, whatever, and we don't care how that parser works internally. That compilation should just work. In this talk, I will show how we compile the disjunctive pattern. The paper also contains some more example metapatterns and how to compile those. So let's introduce some examples of what we can do with concrete syntax metapatterns. So here we have a pattern where this is not a meta pattern yet, this is just an ordinary pattern. We match on classes that have just a single function named foo in them, and that immediately returns some kind of expression. We can make this pattern a bit more interesting by adding a disjunction to it. Now we match on both classes and structs. We can make it even more interesting by making it a sequence pattern. So now I've specified that there can be an arbitrary amount of declarations above and below my function foo. We can make it even more interesting by adding a descendant pattern. Here I've specified that we match on code that, well, the return statement can be in any part of the body. It just doesn't have to be the only statement in the body. And we can keep on going. I can add a patch to it, so I can patch all return statements to, well, something else. In this case, I am wrapping some function called to bar around the expression that I'm matching on. And I can just keep on going. I can add another disjunction here where we have some kind of default case where if we match on a return 0 statement, then we patch that to return -1, and otherwise we do the other case. And the nice thing about this concrete syntax metapattern is that, well, it's all the logic is contained in the pattern itself. It remains readable. Normally, all of this disjunction, the patching, it occurs outside of the pattern, which makes the content or the behavior of your restructuring more scattered than it normally is. Okay. In the remainder of the talk, I will try to explain how we compile this metapattern, concrete syntax metapattern, to an abstract syntax metapattern. But before that, I'm going to do a background section, because we are going to extend some previous work on compiling concrete syntax using black box parsers. So this has no meta patterns yet. This is just, again, terms with holes. This is based on a paper by Rode en Aarse et al. On, well, concrete syntax with black box parsers. And the idea, as I also mentioned in the introduction, is we're going to plug in some black box parser, and we're just going to hope that the compiler is going to work. Well, we're not going to hope. We're going to construct a compiler in such a way that it works with a black box parser. So again, the goal is, on the left-hand side, you have a concrete syntax pattern. On the right-hand side, we have an abstract syntax pattern. How do we get from left to right with just a black box parser? Well, what they do is they first encode the pattern to some parsable string. And in this case, the example, we replaced the meta variable e just with some, just with 0, because 0 is some parsable expression. Now that we have a parsable string, we can actually invoke the black box parser, and that gives us an abstract syntax tree. And as a very last step, we can decode this syntax tree back into an actual pattern by reversing the parts that we have encoded. So we're going to zoom this process in a little bit more detail. Let's start with describing the black box parser interface. So we require the following elements. We need a set of all the syntactic types of that the parser supports. So that can be an expression, name, statement, declaration, you name it. It depends on the language that you wish to support. Next, we of course need a parse function that's given a syntactic type and a string that we want to parse. We need to get the AST. And I've added a note here that the AST nodes should be annotated with location information. They'll become more clear later on. And lastly, we need a function named gen, standing for generate, that takes a syntactic type and generates some string for that type, some parsable string for that type. So for example, if we generate a string for an expression, we can just let it output 0, because 0 is represents an expression. So let's take a look at an example and go through everything step by step. So suppose we have this example and we want to we want to compile this to an abstract pattern. The first step is actually on the user side. We require the user to annotate each meta variable with its corresponding syntactic type. In this case, F should be a name and E is an expression. As a next step, we want to encode this, and that will turn our program into the following. So F gets, the meta variable F gets replaced by some name X, and the meta variable E gets replaced by 0. And that's where we use the gen function that I've introduced before. And the next step, as part of the encoding step, we need to remember everything that we've encoded. So the X was the meta variable F, and the 0 was from the meta variable E. We're going to call this the decoder, because we're going to use this in the decoding step. The numbers there on the bottom left represent the location information. So that is the location in the source string that we have parsed. So in this case, X occurred at index 4 and ends at index 5 in the string that we're going to parse later on. And we need the location information to uniquely identify those parts that we have encoded. So next step, we parse using the black box parser, so we get some AST out of it. And as a last step, we decode it. So we try to identify those parts of the AST that originated from encoded meta variables. So in this case, the name and the integer literal originated from the meta variables F and E, which we can, by the way, detect using location information that the black box parser gives us. And then we just replace them back with the meta variables we used. And this is the basic process from the paper, Concrete Syntax Using Black Box Parsers. Now, in our work, we're going to extend this compiler to also support Metapatterns, and I'm going to show that by adding a disjunctive pattern. So here we have another example where we have a concrete syntax Metapattern. In this example, we match on if statements, where the conditional is the superfluous equals true condition, or, well, the symmetric variant true equals some expression. So the @ symbol indicates the disjunctive operator in this case. Again, we're going to do the exact same steps, but this time we're going to treat the disjunctive pattern here as if it was some meta variable. So we let the user annotate this disjunction with some syntactic type. In this case, the condition of an if statement is an expression. Next step, we encode the entire thing. So we replace the entire disjunctive pattern with 0, because expressions encode to 0. Again, this is our corresponding decoder. So 0 gets decoded to this entire disjunctive pattern. Next step, we parse. then we decode again, so we identify all the parts that originated from encoded elements. We replace them with the original metapatterns. And as a last step, we still need to recursively compile the left and right disjuncts of the disjunction. And then we get the following abstract syntax metapattern. Now, hopefully that made sense, because we're going to make this a little bit more interesting, because we're going to now introduce the invert disjunctive pattern. As I said, the first step was that the user required to annotate the metapattern with a type. That is a bit annoying because it clutters our pattern, but also the user now needs to think about, oh, what is this type? But it's something that should not be necessary. So can we infer this type instead somehow? So we're going to do the exact same thing again, but we're going to skip step 1. And we're going to try to encode this. And we can actually very easily encode this without the type, because we can actually just take either the left-hand side and the right-hand side of the disjunction and use that to encode our entire pattern. So I can take the E equals true and use that as our encoding for the metapattern. Yeah, so we can use the left or right disjunct, and we replace the entire thing with 0 equals true, which represented the E equals true part from before. And now our decoder is a little bit larger because it includes the 0 equals true part. Again, we parse it. We go through the exact same steps. What is happening? Yes. We're going to parse, and we're going to decode again using the same process, and we get the exact same thing back as we had before. We then recursively compile the disjuncts, and well, we get the exact same pattern as we had before, except this time we did not need to annotate it using the type. So that was the disjunction. In the paper, we also introduced some other metapatterns where we describe the compilation behavior. I'm going to go over them very briefly with as much time as I have left. So we have actually 2 variants of the disjunctive pattern in the paper. We have a context-free variant and a context-dependent variant. The example I've just shown you used a context-free variant. The context-dependent variant, one use case for this, what I've written down here, is if you want to pattern match on either classes or structs. And behavior of this metapattern is that we literally unfold every single case here. So we have well, the class foo and the struct foo. We take the entire program and unfold it in its entirety. And this is context dependent because we now take the entire context of the program into account. Why is this useful? Why do we want this over the context-free variant? Well, it's useful if we have no location information. So in practice, we have found that often external parsers that we use, they don't provide location information for every node in the AST, and particularly for keywords. So if I have a class and a struct node in my AST, that sometimes does not have location information, so we cannot decode them. And therefore, we just take the entire program and parse that part. There's one downside to the context-dependent disjunction. That is that we can get an exponential blow-up if we use it too often in one single pattern, because we need to consider every single combination. So if you have an A or B followed by a C or D, we need to consider every single combination of that, so AC, AD, BC, BD, and you can imagine that if you use this a lot, well, there's a lot of time that you need to compile this pattern. Luckily, again, the use cases for this are limited. We're mostly using it to compile keywords, because those have no location information. Another example pattern in the paper is the descendant pattern. The example on the left-hand side is a descendant pattern where we try to match on recursive function definitions. So we have some function definition f, And at any position in the body of f, we look for a function call to that same f again. This is an annotated variant, as in we had to specify the type of the descendant pattern. Well, the descendant pattern represents a list of statements. And furthermore, we needed another type expression that represents the inner type, the type of the inner expression, so the inner pattern. So that's the function called to f. That is an expression, therefore we need the expression annotation there. There's an inferred variant of this that we also introduced in the paper, where we get rid of the outer type that you need to specify, so we can get rid of the statement list here. It's not a nice solution, but it works. Because we need this outer type to generate an encoding, but we can also just try to guess the encoding using some hard-coded set of guesses. So we can, for example, try to guess A, but that's not going to parse. What we can do is we can fill in integer A followed by a semicolon, and then this entire pattern is going to successfully parse. Again, a problem with guessing it in this way is that we get an exponential blow-up if we have many descendant patterns, but in practice we have not encountered examples where we need more than a few descendant patterns in one single pattern. And there's also ways to mitigate it, so we can keep this guess set very small. We can, well, in this example, the A and the int A, they already represent a wide variety of syntactic types that we have. So the A in like a language like C++ represents an expression, it represents a name, it represents a declarator. The int A represents statements, declarations. So we already cover a wide variety of syntactical constructs just by these two guesses. Okay, now going to conclude the talk by summarizing. So we've introduced concrete syntax metapatterns. We like them because it's a very declarative way of metaprogramming. We specifically applied it in the context of software restructuring. We have disjunctions, descendant patterns, and patches. This is not an exhaustive set of metapatterns, but we do believe that this is a representative set. So if you want to add more metapatterns, you can use a similar technique to compile them using one of those. We compile them using black box parsers. This allows us to easily support new languages without too much effort. And we even improved the notation of the metapatterns by using inference on the types. In the paper, there's a more formal presentation of the compiler. Furthermore, we've implemented the compiler and concrete syntax metapatterns as a Kotlin library, and we support C++. So we've implemented the black box parser interface for C++. Furthermore, we have some discussion on several elements. You're also welcome to ask questions about those. So we discussed the effort to implement new metapatterns. We discuss how much effort you need to implement the black box parser. We discussed the problem of the exponential blowup, and how expressive and applicable context syntax metapatterns are in general. So with that, I conclude this talk. Thank you for listening. Are there any questions?
We have about 5 minutes for questions.
Thank you. Maybe I missed it. It seems to me that decode could lead to ambiguities, right? Where you introduce a 0 for an expression, what if there already was a 0?
So we use location information. So we uniquely identify the position in which it occurs in the string that we're parsing. And we hope that we assume that the black box parser also gives us location information for each node in the AST. So we use location information to disambiguate and uniquely identify each AST node.
Is that guaranteed to always work, or are there corner cases?
So there are cases when there can be two AST nodes with the same location. We discussed this in the paper. The default case is that we always take the outermost node because that represents the most general type, so to say. So, for example, declarations are also statements in a context-free grammar. So you can have in your AST, you can have a declaration statement and then then a declaration. Those are two AST nodes that have the same location. We always take then the outermost type.
That's when parsing actually discovers an ambiguity, right? But what I meant is when the expression already contains a 0 and then you have a metapattern E which you replace by another 0.
So then you will have two zeros in your AST that have two different locations. So there's two different zeros.
Hi, thank you for the talk. I was curious about, so there are some languages where the return position in a function is not indicated with a keyword return. It's just kind of the last position in an expression, or all the last positions in all the branches of a conditional. Have you encountered any situations like that, and how would you handle that?
We have not encountered situations like this because we've mostly applied it on C++. C++ does have other ambiguities, but we have not run into those with the examples that we've run. There are ways to mitigate this, so you can. So this would be an ambiguity. So a piece of code can represent multiple syntactic types. The way you could resolve that, which you have not implemented yet, so that's future work, is letting the user explicitly specify the type that a piece of code, the syntactic type that a piece of code has. So then you can explicitly specify, oh, this is supposed to be a return statement or something else. But again, that's not. We currently don't have that, but that would be a way to solve it.
Okay. I have another question. Someone else can go first. Okay, so this is maybe more about future work, but I was curious how you handle scoping for if you're trying to do refactorings. There might be multiple functions called f or foo or whatever in a code base. Do you fully qualify them as a pre-processing pass, or is there some more clever way to do this?
That is a very good question. At the moment, everything is purely syntax-based with these concrete syntax metapatterns. We are working on also supporting metapatterns where you can specify, oh, this f has to reference this function definition f, so you can be explicit about which reference is supposed to reference which declaration. So that also takes then the static semantics of the language into account rather than just the syntax.
Okay, thank you.
So I was wondering about these two different kinds of disjunction, because you just presented that you're putting a lot of effort into inference so that there's less clutter around these types, which kind of refer to the abstract syntax again. But now you have this really an implementation detail leaking into your patterns, right? Because why would I care as a writer of these patterns whether it's context free or context dependent? Can you infer that?
Yeah, that's also a valid point. One solution from a user side would be to just always use the context dependent disjunction and hope you're not using too many of them to cause too much of a performance blow up. In general, we have found that the context-free disjunction almost works everywhere except for keywords. And I think that is something that can be easily taught to someone using concrete syntax metapatterns. But I think this is a fair point. But this is unfortunately not necessarily a problem with the design, but well, it's an edge case that we are able now to support with. And we are allowed to support new black box parser with it. We are to support black box parsers that do not give location information for every AST node. So it is indeed an implementation detail, but we find it a necessary one.
Final question from my side, maybe while the second speaker sets up. So given that you are from Delft, I wondered whether this is planned